What do you say, YouTube? It's Ben from Chemistry Condensed here. This is the second video in a two-part video series on an MIT exam on organic chemistry. This video is going to be going through the solutions to this exam, spring 2005. If you haven't seen my video going through the problems, I'm going to have a link here. I'll also include a link to this in this video to the exam itself, which you can download and go through. I really recommend doing this before watching this solutions video. All right, let's go. Okay, so the first question is, what is the pKa of an sp hybridized carbon atom? And you could just memorize this. So this is a number that some people know is the acidity of the CH bond for an sp hybridized carbon, and it's 25, but we can at least appreciate that it is much more acidic than other forms of CH bonds. So for instance, this number 50, that's the pKa of an sp3. Ooh, do that again. sp3 hybridized CH bond. 45 is roughly the pKa of an sp2 hybridized CH bond, and the trend goes that the more S character, the more stable, in other words, lower in energy, and therefore more acidic. So sp orbitals are more acidic than sp2 and sp3. So we knew the number was less than 45. Maybe 35 was the trick one, but the answer is 25. Okay, question 2. Question 2 had to do with the barrier rotation. So something that made this problem much easier was knowing that roughly the chair flip energy for a cyclohexane is on the order of 10 kcals per mole. And the energies of all of these barrier type rotations are only 2 or 3 kcals per mole. Now, this is definitely maybe not obvious just to people who were looking at this, but definitely when I approached this problem, I immediately saw that there's a pretty significant difference in the energies between these. So I'll immediately box cyclohexane because chair flipping is much higher energy process than just a rotational barrier. If I then look at a Newman projection of ethane in its staggered conformation, and I imagine replacing one of these hydrogen atoms with some other bigger substituent. In the case of propane, which is a methyl, and butane, it's an ethyl. These are really larger groups. It's going to create a much larger clash, and this is going to make for a much higher barrier of rotation. So without having to worry too much about this, I can already say that the answer here is going to be ethane for the lowest barrier. Okay, problem 3 has to do with ranking the substituents in order of priorities. There's just some rules for learning these, and once you kind of know them, all these problems are not so bad. We look at the first atom. All of them here are carbon, so that's the same. We then go to the next atom, and the atoms with higher atomic numbers are higher in priority. So for this one, we have a bromine. That's the highest of all of them, so that's going to be priority 1. We then have 2 that are bound to nitrogen and 1 that's only bound to hydrogen and carbon, so that's going to be last. When it comes to these two, we have to realize that this is actually a triple bond to nitrogen, so it's like 3 nitrogens compared to only 1 nitrogen substituent, so it's therefore higher priority. So this is 2, and this is 3. Question 4 is a good problem that a lot of people get confused about, and it's asking about, if you know that a molecule is an R or an S, does that tell you it rotates plane polarized light? And it's the tricky thing is that R sounds like right, and maybe S is left, and there's clockwise, which is D, and counterclockwise, which is L. A lot of these letters and numbers, and it's confusing. But what I'll say is that the definition of an R and an S is just something we came up with to name molecules. It has no physical basis. It's just like a convention. We could have equally made the convention the other way around. So there's actually fundamentally different, it's a different property from actually how plane polarized light is rotated. There's not a direct correlation between an R stereocenter and rotating to the right. This is 2 different things. So we cannot determine this with the given information. It's an important concept. Question 5 is a pKa question in equilibrium. We have to know the pKa's for this problem, but we can still get an idea for it without them. pKa of phenol is around 10, and the pKa for water is a good benchmark around 16. Here, we already could guess that the equilibrium should lie to the right, given the stabilities of these conjugate bases. So here we have an O minus that's relatively unstabilized, but here we have a negative charge oxygen that can participate in several resonance forms, each of these stabilizing the structure. And this can, you can do these resonance forms around. This should make a more stable conjugate base and therefore a stronger acid. So we would expect the equilibrium to be shifted to the right even if we didn't know the pKa's. The second problem, a little bit trickier because you might think, well, the molecules are charged on the left, so the equilibrium should lie to the right. But you have to actually look at the pKa's here. And the pKa of a carboxylic acid is something that we should know. It's between 4 and 5. We'll call it 5. And the pKa of a protonated amine is around 10. So actually, the equilibrium lies to the left. And it's actually important for dealing with, at physiological pHs, when you have amino acids, oftentimes the nitrogen is protonated and the carboxylic acid is deprotonated. So this equilibrium lies to the left. Okay, question 6. We have an acid-base between an imine and an amine. We draw in this lone pair, grabbing here, kicking electrons back to nitrogen. This would make for a protonated imine and now deprotonated amine. Oops. Lone pair. So again, knowing the pKa's will help with this. You can also know by analogy that, in fact, positive charges on sp2 hybridized centers are less stable than positive charges on sp3. And this is directly analogous to if we, say, compare the acidity of a protonated carbonyl. This is much more acidic than a protonated alcohol. So oxygen here being sp2, much more acidic than an alcohol that is or an oxygen that is sp3 hybridized and being protonated. So because this is a stronger acid, the equilibrium will lie to the left. Okay, for the next one, this is an inductive effect. So we have a trifluoromethyl versus normal acetate. So trifluoroacetate and non-fluorinated. And here, the important thing to notice when we draw in the conjugate bases, oops. Yeah, let's just restart this one. Right, so that's the conjugate base. All right, we have to draw the arrows. Is that these fluorines actually serve to withdraw electron density away, and I'm drawing this dipole that's just indicating that the fluorines that are such electronegative atoms, they draw the electron density by induction, which means through the sigma framework. They draw the electron density away, and this serves to stabilize this negative charge here. Stabilizing a conjugate base makes for a stronger acid, so our equilibrium is going to lie once again to the right. Okay, problem 7 has to do with ranking sets in an order of acidity. So here, right off the bat, my eye jumps out at HCl, so that's going to be priority number 1. And also, this alkane is a very terrible acid, and so this is going to be 5. The carbon ion that results from being deprotonated is terribly unstable, so that's 1 and 5. Maybe trickier here is deciding between the NH, the SH, and the P, the phosphorus H bond, which of these is the most acidic. So if we put up maybe a little periodic table to remind ourselves of the placements of these, it might help. At least it helps me. So we remember that as we move to the right, this is increasing electronegativity. And as we move from oxygen to sulfur, it's an increase in molecular or atomic size. because this is in a new shell. And something we need to know is that as we move to a new shell, there's a much larger radius, and so then the negative charge that results after being deprotonated is much better stabilized on a larger nucleus. So sulfur is a much more stable anion and therefore a stronger acid than oxygen. And when we compare phosphorus to sulfur, because sulfur is more electronegative, it better stabilizes this negative charge that results, and so sulfur is more acidic than phosphorus. So in fact, sulfur here, or I should say sulfur, this thiol is 2, phosphorus is then 3, and this amine is 4. Amines really aren't that acidic. Okay, so if we move on to the next one, this is sort of the opposite phenomenon. So the factors that affect positively charged atoms are the opposite from the factors that affect the negatively charged atoms, like electronegativity and size. But in this case, since we're also looking for the opposite role in the acid-base reaction, that being now we're considering the conjugate acid instead of the conjugate base, the factors that destabilize the conjugate acid are leading to a stronger acid, just like the factors that are stabilizing the conjugate base lead to a stronger acid. So even though the arguments we're going to be using are opposite, the net results are going to look really similar to the first part. So just like in the first part, this case of this sulfur with a positive charge is going to be the least stable, the opposite from sulfur minus being the most stable. So this right away is going to be our most acidic proton. It's the most unstable conjugate acid form. Okay, so then when it comes to the last 4 cases, these are all oxygens with positive charges. And so to compare these, we need to look at the contributions that the resonance forms have. So if we start with the case on the left of a thioester, we can draw a resonance structure where this positive charge is delocalized both on these positively charged oxygen, but also onto sulfur. And we can do the same for every other case where there is a resonance form that further stabilizes this positive charge. When we arrive at the case of the second to the right, where this atom is carbon, there is no lone pair, so there is no further stabilization. This leaves this this positively charged oxygen very unstable, hence acidic. It's going to be our number 2. If we compare the sulfur plus resonance form on the left with the nitrogen plus and the oxygen plus, from the same arguments we just said, sulfur is the worst at bearing this positive charge, hence it contributes the least to stabilizing the oxygen plus, and this makes it the 3rd most acidic. And then comparing nitrogen and oxygen positive charges and which of these are more stable, again, using the same arguments, electronegativity plays, so nitrogen is better able to stabilize it because it's less electronegative. So then oxygen would be our number 4 most acidic, and nitrogen would be our number 5. For question 8, what we really have to do here is label the functional group. Here we have a phenol, here we have an amine, here, 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 and here. We all have peptides, within a peptide we always have amides. And over here, depending on how you wanted to label it, if you grab the carbon, then this is a benzyl group. If you grab just the aryl part, you can call this, an arene. It's not technically a benzyl, or it's not a benzene. It isn't really how you would call it. You would call this just an arene or an aryl group. Here we have a carboxylic acid, and here we have a sulfide. So these are the functional groups in this molecule. For question 9, this is the naming convention that we just sort of have to know. And the first rule for naming hydrocarbons is find the longest linear chain. I count this way, and I get 8. This is the longest chain we can make. If we were to go the other way, then this isopropyl group would be at a higher number. Instead of being at 4, it would have been at 5. And therefore, the ordering, we always try to decrease the numbers of any of the substituents. So this is going to be the order I'm going to go with. So we can see here we have a methyl at 3. We have at 4 an isopropyl. At 5 we have another methyl. And at 6 we have another methyl. So the chain itself was 8, which is an octane. So we would call this, because it's alphabetical, we would call this first the isopropyl, because it starts with an I. And then 3, 5, 6, trimethyl, and I ran out of space, octane. So this would be the name of this molecule. Now for the second one, this is a cycloalkane, so we know right away there's not going to be a longest chain, it's just going to be the number of carbons here, which is 7. We then need to start with the highest priority substituent, which is bromine, so we count 1, and we want to have this tert-butyl group fall in the smallest number, so we count this way. This one's pretty easy. It's 1 bromo, 4 tert-butyl, cycloheptane. And that's it. All right, so for question 10, we need to draw resonance forms and also draw in the lone pairs. So I'll start by putting in the lone pairs on this one. Maybe do these ones a little bit nicer. And we start pushing arrows to try to see where these electrons are going to end up. So we push these down and over to carbon as a first place. And we arrive at this resonance structure. We can now go one of two ways. We can go to the left or we can go to the right. I'm just going to take it to the left. So this pushes up into this carbonyl. I'll draw that resonance form down here. This can then go, well, we could have gone the other way, and so we'll do that now. This one takes you to this resonance form. And finally, these can move up onto nitrogen. So maybe I'll just zoom in so I can see these last structures a little better. Okay, so the last form looks like this. We have our electrons, and the negative charge is on nitrogen now. So if we were to check mark the structures that are most contributing, we have to think, well, which atoms are better at stabilizing negative charges? And just off their electronegativity, we know that oxygen is the most electronegative, so any of those are definitely going to be the most contributing. So that's this structure and the first structure. But the second most stabilizing would be nitrogen, and since it asks for 3, the next one would be this one. So it's all of the structures that had oxygen or nitrogen plus and minus. When it comes to the most nucleophilic atoms, we already really solved this. It's all the sites where the negative charge was localized. This is where the molecule is nucleophilic. So, problem 11 asks us to circle the structures that best represent 2,2-dimethylbutane. For this, it's probably easiest if we convert all of these Newman projections into line drawings and see what we get. So I'm always going to take the atom here and I'm going to put it on the right. I don't really care about stereochemistry since I'm just looking for connectivity. Here, what I get is not what I have on the left. So this is not right. If I look at the one on the right now, I again will just take this atom as this one. Okay, so then I have a, by the way, if this is confusing, I'm abbreviating ME like this. This is my abbreviation for CH3. So if we compare this, we actually see that the atom we start with, if we label the CH3, this actually is our molecule, although it's flipped around. And so we want to say yes, or circle it. Here we're going to put our tert-butyl group, and we have one more atom. And again, we have a tert-butyl with an ethyl chain. This matches the molecule, so this one is a yes. And if we look again at this bond being here, we put 1 methyl, 2 methyl, 3 methyl. This isn't even the right number of carbons, so no, this one's not right. So only the top right and bottom left. If we want to complete now the Newman projection, we just need to fill in the substituents. If this is atom 2, well, they're all methyl, so we'll just put methyl on all of them. Here, 2 of them are hydrogen. It doesn't matter which ones. Methyl will go here. And it's in a staggered conformation. And then the eclipsed conformation is going to be the higher energy conformation. And there is only one possibility. So these are the 2. If we now look to calculate this question, what we need to do is actually know the energies of these 2 gauche interactions and the eclipsed interactions between the 3 of these. We need to know the energies of these. So if we think about the first gauche interactions, there are 2 of them. This would be, in my mind, sufficient to solve the problem, just knowing that there are 2 gauche interactions. You don't maybe have to memorize these numbers, in my opinion, because we have the internet. But for this problem, you would need to memorize it, and poor student at MIT, they have to memorize these things. 2 times the gauche energy, which is 0.9 kcals per mole, gives an energy here of gives an energy of 1.8 kcals per mole for the structure on the left. For the structure on the right, a little more complicated, we have 2 times the methyl hydrogen eclipse energies, which is 2 times 1.4 or 2.8 kcals per mole, but we also have to add to this 1 methyl eclipsing interaction, which is even higher in energy, which is 2.6 kcals per mole. And we have to add these together, and what we get is 5.4 kcals per mole. So then the barrier would be the difference between these 2, and this comes out to 3.6 kcals per mole, which at room temperature is a very achievable barrier for those who are not familiar with kcals per mole. This is definitely rapidly spinning around at room temperature. Question 12 asks us to look at the different conformations of these 2 cyclohexyl rings. We have to first fill in on atom 1. To first fill in on atom 1, we have a CH3 and a CH3, CH3, CH3. Okay, so for A, at the 3 position here, we have a chlorine that is going up and a methyl that is going up. And for this one, the chlorine is equatorial, and the methyl here, did it again. Methyl here is axial. If we then compare the chair-flipped form, we see at the 3 position, chlorine is down and methyl is up. And here again, we have chlorine that is up and a methyl that is up. And it's pretty straightforward to fill in the Newman projections on the right and the left. I won't fill in all the hydrogens, but I'll just fill in all of the important substituents, the chlorine and the methyl. Okay, so now we need to answer these questions down here. It says circle the chair conformation that is lower in energy for each molecule. Well, if we compare, let's say first A on the left, we have 2 axial forms of a methyl and a chlorine, and here we have 2 equatorial, so pretty easy. Equatorial is more stable. Fewer of these 1,3 diaxial interactions. For the structure on the right, well, one of them is equatorial on each and one of them is axial. We need to compare the A values, we can just see that when you have a methyl group here, methyls are like big helicopters. They have 3 CH bonds that are rapidly spinning, and they take up a huge volume, so these are going to clash much worse with a methyl group. So structure down here is going to be a relatively more stable structure. Now, question D asks for which structure is lower in energy, A or B. Well, from the reasons I just said, these 1,3 diaxial interactions, A is going to be more stable, and it has no 1,3 diaxial interactions. Great. Question 13, A asks, label each molecule as chiral, achiral, achiral meso. For this first one, it actually has 2 substituents that are equivalent. And because we have 2 substituents that are equivalent, this is achiral. For the second structure, we're going to need to, well, first of all, this is going to be chiral. And it has 2 stereogenic centers. We're going to need to label the R and the S. So let's do the one on the left first. We take this, we do priorities around this, so bromine would be 1. If we compare, okay, carbon, this one has oxygen on it. That's higher priority than nitrogen, so that's 2. 3, so this is counterclockwise. This is going to be an S. And if we now do this other position, we have the hydrogen coming out at us, but we can still label priorities with oxygen being 1. Comparing carbons here and here, because this has bromine, this has a priority of 2, this has a priority of 3, so it looks like it's clockwise, but because the hydrogen is coming out at us, we have to flip it around. So it's going to be the opposite of clockwise, which is anti-clockwise, which is S. Let's clear that up. So it's S. For the structure on the right away I would sort of look at this question and suspect this might be meso, given that both of these positions have a methyl group and a hydroxyl group. You're going to have to first just draw this in line drawing and see. So I'll draw this one in a line drawing form. So this one is up. And then we just want to rotate, say, this structure on the right so that the methyl's on the top so we can see if there is a plane of symmetry. So we rotate that. And sure enough, what we get out is a structure that has a plane of symmetry. So this is meso. Okay, question 14 asks for the relationship between these 2 molecules. The structure on the left and the right are clearly mirror images, so this makes them enantiomers. For the second one, it's not so obvious. We could assign stereochemistry R and S to each one of these positions, but what we could also do is just make them look like each other or mirror images to see. So I'm just going to flip this Newman projection around. I'm going to bring the atom that is close to us, and I'm going to make it the atom that is further away from us. It does involve a C2, so all of the different positions are inverted. Okay, so then if we want to make the front look like the front of this, we just need to rotate the bromine to be at the bottom position. I'll draw it over here, so we just need to rotate the front so that bromine is here. And if we do that, what we get is CH2OH, and in the back we had CH3HOH. So if we compare this structure with the structure that we have on the right, we can now see that there is a mirror plane. So the front position is the mirror image, and the back position is also the mirror image. This makes them enantiomers. You could have solved this problem by assigning R and S. I just did it this way because it's a little bit faster for me. Okay, for structure on the bottom, we take a look at this structure and we want to have it look like the structure on the right. This will make it much easier to compare To do this, we need to translate this into this stereochemistry. I'll just write in a dash and a wedge, and here if you need to, we use a model kit to be 100% correct. Go ahead and do so. What you'll find is that the OH is here and the H is here, and then for this position, the bromine is the dash and the hydrogen is the wedge. So this is the same stereochemistry, and this one is the opposite. This makes them not superimposable, and they're not the same. They are D for diastereomers. All right, and now that we get to your extra credit question, like I said, this one is a little tricky. It involves knowing the naming conventions for prochiral alkenes, the Cy and Re face, which has to do with, again, the Kohn-Ingold rules. So we assign the priority to be here, 1, carbon 2, and then hydrogen priority of 3. Because this looks clockwise, this would be, the front is therefore the Re face. That is the Re face of carbon 3. And it says that the OH group, or the hydroxyl group, attacks from the backside. So we have hydroxyl group, this attacks, and we say that it attacks from the Re face, from the Cy face. And so we get this molecule. How about I'll draw out the carboxylate, and then we might look at this and say, this doesn't look, this is where it gets a little tricky. This looks like it's, it's no longer an alkene, so then when they talk about Cy and Re, it's a little confusing, or maybe we should assign from the beginning. So this is also in resonance with a enolate form, where this is now a prochiral position, and again, we apply the Kohn-Ingold rules. For naming this, this would be priority 1, this would be 2, this would be 3. So this is a counterclockwise. This would then be a Cy face. And when I'm saying Cy, I mean the face that is on the top. Label the top face. So the top face here is Cy, and the top face here is Re. The attack of the proton comes from the top, although it doesn't really matter. What we get out is 3-hydroxybutyrate. And the stereochemistry here is going to be a dash. And we need to, what do we need to do last? We need to assign this R and S. So one last time, for good measure, we make the OH group priority 1. If we compare this as carbon and carbon with a bond to another carbon, this one only has hydrogen, so this is priority 2. This is priority 3. It looks like it's going to be an R. It fakes us out. The hydrogen is a wedge. We need to flip it around. So this is actually an S. All right, that brings us to the end of this video. I hope you learned something from this solution. I'm going to be making more of these in the future, so make sure to leave a like if you enjoyed the content of this, subscribe to the channel, and as always, thanks for watching.